start. So we're very happy to have Sumit from Kentucky.
University of Kentucky.
Yeah, University of Kentucky. He will tell us about the Floquet EFTs.
Thank you. So I'd like to thank the organizers for inviting me to give this talk here and for inviting me to Korea, which is always a pleasure to come back to Korea. Every time you invite me, I'll come. Okay, I'll come even if you don't. Okay. Okay, so this talk is sort of like in a spirit of an exploration. I'll not ask and try to answer any deep question, but it's more like exploring a set of phenomena which has analogs in CFTs, which one can study in some detail and hopefully will lead to something interesting, maybe even in nature. The talk is about periodically driven systems. So basically you have some system and you have a Hamiltonian which is periodic in time, and so you're sort of driving it all the time. And it is well known that such systems in fact display states which are not possible in equilibrium. And here is an example of something called a Kapitsa pendulum in classical mechanics. So of course, if you have a pendulum and invert it, it's not in a state of stable equilibrium. But if you take the pivot and drive it at some frequency which is large enough, it does become a stable state. And I do have a video to show you that it indeed happens. And it's sort of cool. So that's unstable. No? This is the only fun part of the talk. Why is it not showing?
It's a browser that did you mirror? Maybe you can do mirror display.
Mirror.
Yeah.
How do I mirror? It's a Windows thing. Display. Go to settings and display.
Yeah. Display.
Display.
Think not extend but mirror. Duplicate maybe.
Okay. Keep changes. Done. Oh, there you go. So from the start. Believe me, this is the only fun part. So you can see it's unstable. And now you see what happened. There you go. Okay. Very good. So of course, when you go to quantum systems, in fact, now it's gone again. Okay, good. So when you go to quantum systems, the phenomena actually become richer. There is something called a dynamical localization where effectively wave functions cannot spread out in the presence of a driving in a system where it is not ordinarily localized, but the driving makes it localized. There is a phenomenon which is even more weird, is something called dynamical freezing. You can start with some state, and the system in certain parts, these are typically inhomogeneous responses. In certain parts, it tries to go back to its ground state. So some people call it a Floquet refrigerator for some reason. And then there is, of course, the very popular thing which are called time crystals, which I will not talk about. Many of these features are visible in what are called stroboscopic measurements. So if you have a Hamiltonian which is periodic in time, and if you measure the response of the system at 1 times the time period and 2 times the time period and 3 times the time period and so on, so that's a stroboscopic measurement. And many of the features of stroboscopic measurements are actually captured by something called a Floquet Hamiltonian, which is nothing but the log of the unitary transition matrix between say t to n time. This should be 1 actually, t to t plus 1. So like in one time period, you just write the unitary matrix which does the quantum mechanical transformation as exponential of some constant Hamiltonian times the time period. And this follows from, the reason why it is called Floquet is because of Floquet's theorem. Let me just recap for you. Floquet's theorem is a time analog of Bloch's theorem. So what this says is that if I have a time periodic Hamiltonian, then the transition matrix can be written as a product of two things. The first part, which is called the micromotion part, is something which is a periodic function of time. And the second part is basically the transition matrix over a time period of t. And this object is called the Floquet Hamiltonian. And here is a one-line proof of how this thing happens, which I will not go through. It's exactly like Bloch's theorem in the time domain. Now, typically, it is very difficult to calculate this kind of response in most interesting systems, except in some high-frequency expansions and sometimes a perturbation expansion. And many of the insights people have obtained in real systems actually come from numerical calculations. And the numerical calculations are, of course, always limited by various things, including finite size effects. So wouldn't it be wonderful if we could have some solvable examples of such systems, and we could learn somewhat from these solvable examples? And it would be even more interesting if some of the solvable examples display some universal features of the system which are independent of the microscopic details, and that can possibly happen in critical systems, hence the use of conformal field theories. So some time ago, it was realized by these authors, Wen and Wu, that it is indeed possible to get some insight in a class of such periodically driven systems in 1+1 dimensional conformal field theories. So let me explain what the setup is and the type of things which are solvable, and you'll see why they are so easily solvable, is what is called a square pulse protocol. What that means is that you alternate the Hamiltonian of the system, which alternates between the standard Hamiltonian, which is the dilatation operator on the plane, and the Hamiltonian, which is some combination of this Hamiltonian and some of the other global Virasoro generators. This can be also extended to the other pairs of LQ and L minus Q and L naught. But this is the simplest possible thing. For reasons which I'll not explain, this was actually first studied in the context of on the wall sheet string theory by these authors, and then taken off, applied in something else. And over the past few years, there has been a pretty large literature in 2D CFTs which are driven in this particular way, and I've listed just a few papers. It's a kind of mixed community between high energy physicists and statistical mechanics, condensed matter physicists, and it's actually much longer than this, several hundred papers about this. And let me first describe some of the phenomena which you observe in such things. Now, there is a particular limit of this kind of Hamiltonian, which is called the SSD limit. It's called sine squared deformation limit. This is the limit which happens when this coefficient here is 1. And in that limit, it's called sine squared because Hamiltonian can be written as sine square x upon 2. X is a coordinate on the circle times the energy density. Alternatively, such a CFT can be thought of as a CFT living in a non-trivial metric, which is of this form. Now, this kind of drive has a rather peculiar feature, which also explains some of the behavior which is shown in this response. And one feature is that because the Hamiltonian is a combination of L1 and L minus 1 and L0, the vacuum, the conformal vacuum is invariant. However, other states evolve differently. The spectrum is completely different compared to the spectrum of L0 plus L0 bar. And as a result, there are many quantities which show a non-trivial response. And one of the simplest quantities is, for example, unequal time correlators. Because if you do things at unequal times, it's going to excite the entire spectrum of the theory and we'll start seeing the difference. The good thing about this and why this has been such a popular activity is, of course, because the Hamiltonian is always a linear combination of these conformal generators. So time evolution at each such step is nothing but the corresponding conformal transformation where the time itself is the parameter of the transformation. So the using standard technology of CFTs, you can calculate many things. Let me just give you some flavor of the kind of results which you get. And first I will tell you the result of not a periodic drive, but just a quantum quench. Namely, you start with this Hamiltonian H1 and suddenly change the Hamiltonian H0 and suddenly change the Hamiltonian to H1. Okay? What one finds is that in such a situation, if you measure things at some late times, what you find is that when this parameter theta is finite, one finds that the various quantities eternally keep oscillating in time. The period of oscillation is determined by some parameters which are there in the Hamiltonian. On the other hand, in the SSD limit, where you go to the theta going to infinity, where tan hyperbolic theta is equal to 1, there are no oscillations, rather than at late enough time, one gets decays. The unequal time correlators in this situation, they decay with time. So people call it a heating phase, though it's really not, anything is not being heated up. And one of the things that's a bit peculiar about this notion of heating is that typically when you have a system and you light a fire in the middle of the room and the whole room thermalizes, then of course, after a time, everything becomes homogeneous. The temperature is the same everywhere. Over here, the system remembers the original inhomogeneity. So the energy densities of, say, excited states sort of get localized in some regions. So that's one interesting part. The similar thing happens when you calculate something like an entanglement entropy of an interval. And what one finds, and this is taken from this paper, is, so there are, in this particular example on the circle, there are 2 points where there is concentrations of the energies. And if your interval, which you're using to calculate the entanglement entropy, lies in that region, then what you find is that the entanglement entropy after a time rises and then saturates to some value, as would happen for system which is thermalizing. On the other hand, if it is in any other interval, what do you find? is that the entanglement entropy in fact goes to 0 and basically assumes a vacuum value. If you do actually a periodic drive, then the following thing happens. Now, as I said, the previous situation is having phases where you can have oscillations or phases where you can have decays. I'll call them equilibrium phases because it's the response of a system with a constant Hamiltonian, maybe with an initial state which is non-trivial. Okay. In a periodic drive, what happens is that you can change the amplitude and the periods of the drive to drive the system between heating and non-heating phases. And here is a kind of a result where in such a drive, this is the one of the time intervals, this is the other time interval, and you can see that by changing those, you can go from non-heating to heating phases. So for that reason, because this is a feature only of the driving, doesn't happen in equilibrium, these are called dynamical phases, phases which do not exist in equilibrium. In the heating phase, the total energy of a primary state and the entanglement entropy grows, and in the non-heating state phase, the energy and the entropy oscillates. Now, people have done this with an initial thermal state, and there one finds this feature which I sort of briefly mentioned, that you start with a state which is thermal at some temperature T, and you do this driving, and you can adjust the frequency where there are parts of the system which actually cools down rather than heating up. That's why it's called a kind of a Floquet refrigerator. So we were curious to know whether some of these properties which I just mentioned are special properties of two-dimensional CFTs, which are of course very special, or whether or not you get something similar in higher dimensions. Of course, doing higher dimensional conformal field theories are much more difficult than doing 2D CFTs, but we'll see how much progress we can make. So what we are going to do is to describe this kind of thing in 2+1 and 3+1 dimensions. You will see why we are only doing 2+1 or 3+1. In fact, we're going to work with a 3+1 dimensional system. The result for 2+1 can be obtained by choosing one of the angles to be the one of the azimuthal angles to a particular value. And we are going to, and as is usual in conformal field theory, we'll start working in an Euclidean space and obtain the Lorentz transformation by an analytic continuation and a Weyl transformation, which is the standard Weyl transformation. So just for the record, here is the conformal algebra in, is it gone? Yeah, it's okay? Yeah. This is the conformal algebra, and these are the representations of the algebra on the plane. You had a question here. Right.
You can inject energy, you can remove energy. How much fine tuning gets involved in making sure that your state don't just endlessly pump energy?
Yeah. So, for example, in the 2D, since we have talked about 2D, we'll come higher dimensional results. So here it is that the tuning you're doing is changing the frequency. In this case, of course, a very simple protocol of constant, stepwise constant Hamiltonians. And you can see that you pick some value of, say, T0, some value of T0 or some value of T1. You can keep changing the other value so you can transition from one phase to another. And there is a kind of a dynamical criticality in between those phases where the decay of, say, correlation functions is not exponential but a power law. But we will see this actually very clearly in our context. Okay. The way we are going to do this is the following. We want to have the same philosophy namely the Hamiltonian, will be some conformal generator, some linear combination of the basic generators which you start from. And of course, for example, in 4 dimension, there are 15 of them, so there are a lot of them. And we want to cover the entire conformal group by starting with SU1, 1 subgroups of it. It's sort of like covering the rotation groove by U1s by the Euler angles. And there are many of these SU1, 1, subgroups of the conformal group, and we are going to switch one for the other and go on the other. So as a result, the hope is that we haven't been able to do the most general thing. We will show what we have done so far. And so we are going to get more and more generic members of this conformal group by doing that. In each such step, we are going to use a Hamiltonian, which is the standard dilatation. These I's are just conventions, the way the hermiticities are chosen. I mean, you need that I here. This is the dilatation operator, the boosts and the momentum operators. This is the Hermitian combination of those. And our time protocol would be having one such Hamiltonian with one value of that parameter, switch to another Hamiltonian with another value of the parameter, switch to another Hamiltonian with another value of the parameter, come back down and keep repeating in time. Okay. And we are going to get, for example, if I want to get the response at this time, I'll first do a suitable conformal transformation which corresponds to this, then with this, and then with that, and compose them to get the final result. So that's the general idea. Now, in this case, if we take these three, the example which I just showed, 3 different Hamiltonians which belong to 3 different SU1, 1s, and of course, if you compose them, the Floquet Hamiltonian, which is defined in this following way, so the period is T1 plus T2 plus T3, will in general be a linear combination of all the conformal generators. Okay. So that's the strength we want to use. And just for the record, if you want to know what are these Hamiltonians look like on the R cross S3, it's energy density multiplied by a factor. This y mu are the embedding coordinates on the sphere. So this part is basically some cosine theta of some azimuthal angle. Okay. So before going to the drive, let me discuss some properties of the individual Hamiltonians, because each of these Hamiltonians are a bit unconventional in CFT. So let's discuss some of the properties. It turns out that there was a parameter which each of these Hamiltonians, which I call beta, it has an index mu because it depends on which combination of k plus p I am taking, okay, which is k1 plus p1 or k2 plus p2 and so on. It turns out that when this parameter is smaller than 1, there is a unitary transformation which relates that Hamiltonian to the standard dilatation operator. Okay. So as a result, the physics will be pretty much like that of a dilatation operator. What this transformation, of course, means is that you can choose a new set of coordinates in which this entire generator becomes basically del t in the new coordinates. So this you can think of as some kind of alternative quantization of the same theory. Oops. Okay. When beta mu is greater than 1, however, there exists another transformation which maps that Hamiltonian to what sometimes people call the Lushar-Mach Hamiltonian, which is the sum of k plus p. Okay. So the physics of that would be pretty much like the physics of k plus p. When beta mu equal to 1, which is an interesting case, there is no such transformation. So that's a kind of a standalone Hamiltonian by itself. These behaviors actually have a geometric significance. If you consider the space on which the conformal field theory is living, each of these Hamiltonians would, of course, define a vector field. And you can ask, is the vector field time-like everywhere, or are there horizons? And then you can show with a very short calculation that when this parameter, so this is the, if I take that h mu of beta mu I've taken for h0 of beta 0, the norm at that vector field just turns out to be this. So what this shows is that when this parameter is always smaller than 1, this vector field is always time-like. When this parameter is bigger than 1, there are horizons, and these horizons are with like a non-zero surface gravity. There's some kind of temperature associated with those horizons. So in a sense, this effect in those cases are pretty much like the effect in Windler quantizations of usual theories. When beta 0 is equal to 1, these two factors are the same. You have a double zero, and what you have is an extremal horizon, which has zero surface gravity. So what is the effect of this? So this horizon, yeah.
Beta bigger than 1 actually makes sense.
Which one? The beta bigger than 1? Why not?
Yes, the T naught naught is flipping some. You have a region where it's going to be negative to be positive.
Yeah, so there's a region where it is time-like, that Hamiltonian is time-like. There is another region where it is space-like. So the physics is restricted to the region where it is time-like. And that's what will show up in the results. That's what I meant by having a horizon. Okay. These horizons must manifest themselves to the response of a quantum quench or to a periodic drive. So we need to learn how to calculate the response under such a transformation. And if you did the same thing for 1 + 1 dimensions, you will be doing some complex analysis. All these transformations are Mobius transformations, and you can use the whole power of complex analysis as you do in usual 2D CFT to calculate things. So you might wonder, what is the analog of complex analysis for higher dimensional conformal transformations? And at least up to 4 dimensions, it turns out to be you replace the complex numbers by quaternions. So let me explain how that works. So let me start with R4, and you define a quaternion, of course, in this following way. I mean, you see the 3 Pauli matrices, you represent the 4 coordinates in terms of a 2 by 2 matrix. You are using a notation where this quaternion comes with an index. That index just denotes which x you have put proportional to the identity matrix. Okay, so of course, having these different QRs are completely equivalent. I mean, it's just different representations of the same thing. It's just convenience which you want to use. See, in terms of these things, for example, the 2-point function of conformal operators is given by an expression, is a determinant of this of the matrix which is obtained by taking the difference of these quaternions. In this formalism, a general conformal transformation is given by something which pretty much looks like in 2D, except the parameters themselves are quaternions. So this is the general rule with some 4 quaternionic matrices, 2 by 2 matrices. Everything is a 2 by 2 matrix here, and there is a determinant condition which is like the standard AD minus BC equal to 1 becomes this. And you can do the counting. There were 16 to begin with, this one condition. So that reduced right to 15, and that's of course the number of parameters in SO4, 2. Furthermore, under these successive transformations, if we do it once and if we do it the second time, this matrix just gets multiplied like matrix multiplications. Again, pretty much like Mobius transformations. This I have done on RD. If you want to talk about real-time dynamics, you have to, of course, first do a while transformation to S3 cross R and then do an analytic continuation there. And it turns out if you do that, the condition for this to work is that this A and D no longer need to be real valued quaternions. They can be complex valued quaternions with those hermeticity conditions, A equal to D dagger. It's like the connection between SL2R and SU1, 1. Good. That's so much as the formalism. A great simplification happens, and I don't know the underlying reason of why this happens. It's just, we just figured out that this is what happens by direct calculation, is that suppose I take an SU11 which is generated by D and the K mu and a P mu with some value of mu, say D, K1 and P1. If I choose the quaternion which I label by Q1, namely the X1 multiplies the identity matrix, then these 2 by 2 matrices, they just become proportional to the identity matrices. So they just become numbers. And then it's very easy to calculate what's the effect of a conformal transformation. So here is an example of what you would get. Right. So here is an example of what you will get if I do a time evolution with one of these Hamiltonians. And so this Hamiltonian is characterized by a value of beta, which is sitting here. There's something which is square root of 1 minus beta square. And as a result, the result of this transformation, as I said, the time evolution with that Hamiltonian is equivalent to a conformal transformation with time as that parameter. And this is that conformal transformation which happens, where the time dependence is given by the time dependence which are there in A and B, which are written out here. As you can see from these expressions, these are all periodic functions of time when beta naught is less than 1, and they are hyperbolic functions when beta naught is greater than 1, and they are linear functions when beta naught is equal to 1. So this is the basic reason why these 3 different classes of Hamiltonians have 3 rather different behaviors under time evolution. So here is an example of what this leads to. Suppose I take this Hamiltonian and calculate unequal time correlators. And this is what the result is. Beta less than 1, the correlator oscillates in time. Beta greater than 1, it decays exponentially with time. And beta equal to 1, there is a power law decay which is linear in time. I'll call them equilibrium phases, which are associated with these Hamiltonians, because it's just a time evolution with a non-standard Hamiltonian. If you want, these are some explicit expressions for these things. Okay. So there are some pictures of these correlators, I mean, basically plotting out what we got from this calculation. As I can see, that's a function of time, periodic behavior, and an exponential behavior, and so on. You could see the same kind of effect in other interesting quantities. As I said, that in this setup, we are using if I start with the vacuum state is actually invariant. It is no longer the vacuum of the full Hamiltonian, but the state itself is invariant. But if you start with the primary state, you get something more non-trivial, and you can calculate something people call the fidelity, which is the amplitude to return to its original state, and you again get the same kind of behavior. Okay, I'll not show you these pictures. So let's now finally come back to periodic drives. The simplest periodic drive is something where for a period T1, I evolve with the standard Hamiltonian, and in the next period, I evolve with some other Hamiltonian. Okay? And you repeat the process indefinitely. At the end of n such periods, you're going to get an evolution operator which looks like this, which is, some T1, T2, keep going, so the whole thing raised to the power n. And this entire complicated expression would be written as a Hamiltonian, which is called the Floquet Hamiltonian. This Hamiltonian is actually constant in time. It's not time dependent. The reason I've written it as a function of t is because the Hamiltonian is different for different time periods. I mean, it depends on what time period you are taking. That's what the thing is. Under single period, this is what the transformation is. You can see these expressions for beta greater than 1, beta less than 1. And here is the interesting part of the story. You can now iterate the transformation because you have an explicit form of the transformation. And as you iterate the transformation n times, what you find is that the original quaternion, which is just a point on the plane, has moved to a new point on the plane, which is denoted by q naught prime, which has this following form. If I make a measurement, like every time period, that's a certain number of time periods, which we call a stroboscopic measurement, we would be interested in the behavior of these coefficients as a function of the number of time periods. We want to look whether after a certain number it is repeating itself or not. And now we find, depending on this quantity, which I have defined as lambda e, which is arc cosine of the real part of one of those coefficients, depending on that, you can get either trigonometric functions or you can get hyperbolic functions. So when this is less than 1, this entire object is AR is less than 1, you get a trigonometric function as you got. So you get a periodic response to the system, but the period has nothing to do with the period of the drive. It's a very complicated function of the periods which are involved in the drive, amplitudes which are involved in the drive in a rather complicated way. So the condition of getting a periodic response or an oscillatory response in a periodic drive is rather different from what you get by evolution of a single Hamiltonian. So you can have a single Hamiltonian which has a certain behavior, whether oscillatory or not. But as a part of a periodic drive, what you can do is you can change the period of the drive itself to drive the system in a completely different phase. I mean, that in fact is the main phenomenon. So let me again mention what happens when this parameter is equal to 1. You have something which are linear in n. When this parameter is bigger than 1, you get something hyperbolic in n. And of course, all these things will enter when you calculate physical quantities like fidelities or unequal time correlation functions will express itself as oscillations or decays of this quantity in this stroboscopic time. Good. This story so far is pretty similar to 1 plus 1 dimensions because we have basically done a SU1,1 drive. I mean, there's nothing, it's all group theory in a way. In fact, whether or not you have a response which is oscillatory or decaying is completely characterized by the type of conjugacy class of this SU1,1 matrix. But we want to get something beyond that in higher dimensions. just for the record, it is actually possible to calculate this Floquet Hamiltonian in this case, and these are these following expressions, which we won't be able to do very soon. And here is a kind of a picture of that kind of drive. T1 and T2 are the time periods. I think these blue ones are what is called a non-heating phase. The white ones are what I call a heating phase, and you can go one from the other by just simply changing the frequency. But as I said, we want to explore phenomena which is different from 1 + 1 dimensions. So we want to go to some more general drives involving other elements of the full subgroup SO4, 2. And here is one example which is analytically tractable. So you have 3 elements to each of these periods. They are given by 3 different types of Hamiltonian, H, H1, and H0, and you keep repeating them after the time. Each of these are like different SU11 subgroups of the SO4, 2, and the idea is to sort of combine them to obtain the Floquet. Yeah. Yeah, so I'll come back to this. I don't know what the conjugacy classes are in Lorentzian signature. I know what they are in Euclidean signature. Yeah, it would be, I mean, of course, yeah. So this is the result for what happens when you do for a single cycle. The difference from the previous case is that these coefficients are themselves now 2 by 2 matrices. In this case, however, we couldn't figure out a way to easily determine the Floquet Hamiltonian because, you know, basically because the Baker-Campbell formula is known for SU1, 1, at least I don't know what it is when you go to beyond that group. But here is what we decided to do, is that we said we have this nice expression of this transformation in terms of a 4 by 4 matrix. I mean, each element here is a 2 by 2 matrix. How about just diagonalizing this matrix? Because once I diagonalize it, of course, the iterations are very simple. You just raise the eigenvalues to them power. So that's what we did. And here are the 4 different eigenvalues of that matrix. These P's and the Q's are, you know, are defined here in terms of the parameters of the drive. Doesn't matter what the details are. And after n such periods, the n dependence of the quantities would be simply those eigenvalues raised to the power n. As you can see, you will get an oscillatory behavior only if these are pure phases. All of them have to be pure phases. Because then, you know, you'll be sort of moving on a circle back and forth. Okay. If any of them is not a pure phase, then you wouldn't get this oscillatory behavior. So let's see, when do we get such pure phases? Something happened, sorry. So here is a classification of the phases of the system. These are the dynamical phases of the system. The response is purely exponential when this object here and that object are both greater than 1. These are the objects which appear in the expression for the eigenvalues. So if this object is bigger than 1, this of course is some real number. So it's some real number raised to the n. So that's not oscillatory. When both of them are smaller than 1, then you get a purely oscillatory phases. You'll get a parabolic phase, namely power law decays, when both of these are exactly equal to 1. And if one of them is smaller than 1, the other one is bigger than 1, you get what we could call a damped. In some directions, it's decaying in the space, in the other direction is oscillating, and the net result is that you have it's like a damped oscillations, if you wish. How easy is it to get such an oscillatory phase? I mean, in a sense, it's quite natural for a driven system to go into a phase where things decay as a function of time. It's rather unnatural for it to get an oscillatory phase. And that's one of the questions we wanted to ask, because in 2D, it's not that hard to get an oscillatory phase. So here is a diagram. Let me read this. The blue regions indicate when two of the eigenvalues are pure phase. The orange regions are when the other two eigenvalues are the pure phase. And these are the intersections. So these are the only regions in this space of frequencies, if you wish, where you get an oscillatory phase. Okay? This is very different from what we had earlier obtained, where there is this entire connected region, goes all the way to infinity, where you can have an oscillating phase. Okay. So it has become already much more difficult. I mean, I think this got to do with the question of fine tuning, much more difficult to achieve an oscillatory phase.
But I mean, something that's strange to me, it seems like the criteria that you need to satisfy are completely theory independent. Like it's fine tuning the perturbation, but it's independent of the theory.
It's completely independent of the theory. Yeah, I mean, of course, it's just a property of the CFT. It's only a property of, the parameters which I call the amplitude of the drive and the time periods. I mean, it has nothing to do with where that CFT comes from. Right. And that was part of the motivation, that you want to do something which is independent of those details. When you have more general protocols, which cover more and more of the conformal group, we were not able to analytically find expressions for these eigenvalues, because it becomes, it's a general quadratic equation. It's very difficult to have solutions, but we could do it numerically. And as you do it numerically, what you find is that the more and more you cover the more generic drives belonging to the conformal group, it becomes harder and harder to get an oscillatory phase. So the general, at best, what we can have are these damped oscillations, where some of the phases are purely oscillatory and some of them are not. And of course, one would expect that these are related to the conjugacy classes of the bigger group. For SU1, as I mentioned, they are in one-to-one correspondence to the type of conjugacy classes of the SU11 matrix. And if any of you know about this, it would be useful. We have been able to find a mathematical literature where there is a classification when you have an Euclidean space of namely of the group SO5, 1. We tried to stick in eyes at various places to obtain SO4, 2, and it doesn't seem to work. So I think there's something non-trivial in the mathematics which we don't understand. Okay. So that's something we want to figure out. In the final few minutes, I should, yeah, good. SO41. Yeah, anything with, yeah, SO51, SO41 can be obtained from the SO51 classification by setting some parameters to 0. But the moment that comma becomes comma 2, I mean, beyond just, just SO1, 2, I mean, we couldn't find anything which is. Why did, I think these are mathematicians interested in conformal geometry, and this They worked it out in the language of quaternions. And quaternions was, I think, Feza Guerce's favorite. And so I think it's sort of like, his followers, followed that up, but they were mostly interested in the mathematics of the Euclidean signature, but not on these kind of things. But I think we'll probably, with a bit of thinking, we'll be able to figure it out. Now, I talked about horizons in the CFT under evolution by a single Hamiltonian. I mean, the idea is that if you have a Hamiltonian that defines a vector field, you want to figure out whether the vector field is time-like everywhere, where there is a sensible meaning of time evolution, or are there horizons which divide up the space? And you can ask, what is the corresponding statement in a periodic drive? In a periodic drive, one is mostly interested in stroboscopic measurements, namely measurements after certain integer multiples of the time period, in which case you can certainly go ahead and look at the properties of the corresponding vector field which corresponds to the Floquet Hamiltonian rather than the dynamical Hamiltonian. And not very surprising, what you find is that, again, the Floquet Hamiltonian have horizons when you have a heating phase, and they don't have horizons when you are in an oscillatory phase. It sort of reinstates that philosophy. So let me finally come to holography. Everything I said here was just a property of the CFT, and for holographic CFTs, they should have a bulk dual. Now, in the case of the vacuum, when you start out from the vacuum, the state was invariant. So the bulk dual would be locally ADS. I mean, nothing could be different. So what is the thing that is different which is causing all this? Okay, if ADS remains ADS, what is it? I'll come back to the question in a minute, but let me just make a comment that in the ADS-CFT correspondence, those horizons which you find on the boundary, they are horizons associated with the killing fields on the boundary. And of course, all these killing fields have an extension into the bulk. I mean, for pure ADS, you know what those extensions are. And so you can go ahead and figure out, what those horizons are doing in the bulk. And we did that, at least for up to the case of ADS5, we did that. And again, what we found, what I just said, that whenever there is a horizon on the boundary, that the system is in a dynamical heating phase, it extends into a real horizon with a temperature in the bulk. What is more interesting is that what is it that causes the difference? And this is one of the main reasons. I said time evolution is equivalent to a conformal transformation. I mean, whether it is periodic or not, it's always some conformal transformation. So what this means is that if I calculate a correlation function with this modified Hamiltonian, that corresponds to the standard correlation function in some new coordinates, which is obtained by the transformation. And then, of course, there is a factor which comes raised to the power of conformal dimensions. If you think of this formula in the context of ADS-CFT, where the left-hand side should be obtained as by the extrapolate dictionary as a bulk correlator with some power of the radial cutoff here, which I call R nu, then you immediately realize that this new radial coordinate which is necessary for this is related to the old radial coordinate by a function which depends on the boundary coordinates. So what this means is that, yes, it is still locally ADS, but the different foliation of the local ADS, of the ADS space. Of course, in ADS-CFT, it's very well known that if you have different foliations of the same geometry, the boundary physics is very different. And that's what is being manifested here. One of the things which we are in the process of figuring out in higher dimensions is it's a case of a finite temperature. In a finite temperature state is of course not invariant under any of these Hamiltonians, it's going to change, and so it will be a lot more non-trivial. Of course, in 1 + 1 dimension, what would it correspond to is to have a start with a BTZ black hole and figure out what happened through the BTZ black hole. And this, a lot of people have done that. You know, there are many papers of this. And what one finds is that the horizon of that black hole suffers oscillations under this periodic drive when this parameter is smaller than 1. And people have looked pretty much in detail for beta naught equal to 1, which is the SSD drive, where the horizon moves sort of bodily, goes to the boundary. You know, it's sort of, it's a deformed horizon going to the boundary. Of course, one of the things which makes these calculations possible is that BTZ black hole is, of course, locally also an ADS3. So you can figure out a lot of things, and that's not the case for higher dimensional ADS. But I do believe there may be a way of figuring out what the dual of that is. We haven't done that yet. And I believe that this will actually tell us something interesting about black hole physics per se. I mean, it has already taught us something about BTZ black holes, how they behave under these periodic perturbations on the boundary. And I think it will be a lot more interesting to figure this out in higher dimensions. We don't have any, any firm results yet, but I think that's something which I would really like to understand. So I think I'll like no conclusion, because there is no conclusion. So I'll just say that I think it should be a lot of fun to figure out these very non-trivial dynamics in these systems. I mean, both from the field theory point of view as well as from the gravitational point of view. And I hope that I'll have some fun, I mean, in the next couple of years. Thank you very much. Yeah. Yeah. Yes, it's a technical limitation. I mean, because this, I mean, technically, because in these quaternions, it just multiply matrices, it's easy to figure out things, but the principle is the same for any number of dimensions. You just have to figure out any of doing it. So I think the quality of new things at above 4 dimensions, I don't know. I think it will be pretty similar to 4 dimensions. I think something new happens when you cross 2 dimensions, because there are this extra phase which happens, which didn't happen in 2 dimensions, when namely this phase which is, what is it called, associated with the loxodromic conjugacy class of the group, which manifests itself as these damped oscillations, and the fact that it becomes rarer and rarer, a lot more fine-tuning to obtain an oscillatory phase. It's in a sense, hard dimensions are more natural than 2 dimensions. I mean, this is sort of what you would sort of expect in real systems under a periodic drive. You don't expect it to, you know, oscillate back, except if there's something like a time twister or something. Possibly, possibly, I think, yeah. Why not? Yeah.
1+1, these conjugacy classes were also interesting, not necessarily for the periodic writing, but for example, for this conformal transformation of mimic going through the vacuum for something like heavy state,
Right, right.
Do you think that there's something like this that could happen in higher dimensions where there's some things that are like hyperbolic conjugacy?
I think so. I think so, yeah. Yeah, I think, again, it's a technical thing that, I mean, these quaternions are sort of mirroring what complex numbers do in 2 dimensions. So I think many of those things would become, some of people haven't used this very much. I don't know why, but I think it's, huh? Yeah, they're not variant, but nevertheless, I think it does share some properties with complex numbers, which could be useful in other contexts. I'm pretty sure of this.